Welcome back. Today we're going to talk about the Ritz series and give an introduction to continuous systems and show how the Ritz series can be used to come up with models for continuous systems. We'll start with an example to kind of give you the framework for continuous systems. So imagine our continuous system was this rod. That's about the simplest continuous system. And when we say rod, we're talking about extension or axial motion. If we called it a beam, we'd probably mean that it was bending motion. So suppose we're interested in vibration of this rod. So we apply a force and we want to know how the rod deforms. It's a continuous system, so at every point on the rod we could have a different degree of freedom. Or in other words, u, the displacement, is a function of both position and time. So two-dimensional. And one way we could model this would be to break this rod up into a certain number of masses. Let's say we broke it up into 4. So we divide it into 4 pieces. We call each of those a mass. And then we could create a lumped model such as we're used to. So we'd have these 4 masses, and then we'd need springs to connect them. And so if we call the stiffness of those springs K, that would represent the stiffness of the material between these 2 points. So if we had a chunk of material with that length and we were putting in an extension, right, that would be our spring. And then the mass would be density times the volume of the material there. So notice this spring is shorter, so it would actually have twice the stiffness of the others. But anyway, we could do this. We could assign a degree of freedom to each mass. And if we were then to consider the frequency response of the system, and I guess let's just talk about like a transfer function. Like say we apply a force at the end, and we're interested in, say, the response at the end, x4. So this could be h41. Alright, so if we did that with this 4 degree of freedom model, we would have a system that would have 4 modes, right? And then at some frequency we'd reach the frequency of the last mode, and there would be no other resonances after that, right? So that would be our 4 degree of freedom model. What would happen if we instead discretized it using 8 degrees of freedom? 2 things would happen. We would get more accurate pictures of these modes. So maybe, some of these frequencies would change a little, right? And we'd introduce 4 additional modes, right? So this would be the n equals 8, where this was the n equals 4 case, right? So a continuous system model would have more degrees of freedom, and if we allowed the number of degrees of freedom to go to infinity, then the highest frequency in the system would go to infinity. But we know that in practice, our forcing functions tend to have kind of a limited bandwidth, right? At some point they go to 0, and so we only need enough degrees of freedom to cover the bandwidth of our force to be able to get accurate predictions of the response. So this is what allows us to to be able to create models for continuous systems, to approximate an infinite degree of freedom system with a finite number of degrees of freedom without really losing dramatic accuracy or anything. And the Ritz series is a method that allows us to do that. So from your reading in the book, you should have hopefully captured this key idea of the Ritz series, which is captured right here, which is that we're going to approximate U, which is this infinite dimensional in both space and time, right? We're going to approximate that with a finite number of basis functions, and these are continuous in x. So you could say that these are infinite dimensional in x, and the degrees of their amplitude, each basis function has an amplitude, and those are like our usual x's, our usual coordinates. Those have, infinite dimension in time. So it's like taking a system, taking a response and approximating it with a finite number of shapes. And this is very much like modal analysis, right? So sometimes this is called the assumed modes method. But the Ritz method is a better name for it, because you'll see later that that's a little bit of a misnomer. It doesn't really capture the spirit of what we're trying to do. All right, so just to drive home the point, let's consider one other example of this. A really simple example of a Ritz series analysis. And just to kind of get you familiar with the concept. So let's say we had our favorite 2 degree of freedom system. 2 degree of freedom system. We have masses 1 and 2. Let's just have the masses all be equal. And the springs all equal. And we have 2 degrees of freedom here, x1 and x2, right? Let's say we want to approximate this system. This only has 2 degrees of freedom, but let's say that we approximate u of x of t with a basis function psi of x, and just one of them, and then we have q1 of t. And let's say, for example, that psi1 was a function where both masses displace the same amount. So, we think of it as a shape function. If we plotted psi versus x, well, in this case it's a discrete example, so we just have these 2 points, right? So it's kind of a trivial case. But anyway, if we did that, and then we derive the equation of motion, notice then that that is the same as kind of lumping both of the masses together into one rigid mass, 2m. So by inspection, we could see that the equation of motion for this system would be 2m q1 double dot plus 2k q1 is equal to 0. So, and then we could find the natural frequency for the system. And actually, it ends up being a good estimate of the actually an exact estimate of the first natural frequency that we get if we did this. Alright, so that's the idea, is we take a system, we're simplifying the system down by prescribing a finite number of ways that the system can deform. Alright, so let's talk about how you would do this in practice. So again, this is just an example this is not how we use the Ritz series typically. So what do we actually do in practice? Well, there are a few steps. First, we make this key assumption. We assume that the displacement, or later we'll extend this to bending, can be approximated as a summation of basis functions psi j of x, qj of t. And for the purposes of our class, I'm not going to talk through all the mechanics. That's covered in the book. You can read up on that. But basically, the next step then is to go to the book and to look at the formulas for the terms in the stiffness matrix and in the mass matrix, right? To look those up. So like in this previous example, this would be like the M11 term, the K11 term, right? We figured those out. In the book, you would do this using the various formulas that are there. So for example, this is for a rod, axial motion, like we've just been talking about. Using principles from mechanics of materials, Ginsburg has derived these formulas that tell you the j comma nth term in the mass matrix is the product of the jth and the nth shape functions. We have the density and the area, and then we have to integrate from 0 to L, right? So, so we can plug in here and we can calculate. We just have to evaluate some integrals and we can get those terms, right? These terms are for discrete masses. So if we added a mass at the end of our rod, here we're evaluating the basis functions at the place where the mass is. So, you know, if we have a rod, and we have a big mass here on the middle, this xm would be the location of that mass. And similarly, we could attach a spring there and use this term and so on. Alright, so these are the formulas that we can use. And again, read up in the book to kind of see how they're derived. We won't cover that in lecture. I should note there are a couple typos that I've noted on the slides here. Most important is this one on the stiffness terms for the stiffness matrix for beam and bending. So those are corrected here in the slides. Alright, so let's go back to our example. So that's the second step, is we go to the book and we get those terms. For j equals 1 up to n, up to however many terms we need, right? And for n equals 1. So depending on what approximation what level of approximation we want. Alright, once we've done that, then we can just assemble the equations of motion. And our equation of motion will be defined by those terms that we've just found. And we'll have also then the amplitudes of the basis functions as our generalized coordinates, right? So here I'll just call that the K matrix. We'll have Q1, Q2. And in the book it also gives formulas for how the forcing comes in. And I believe those are called Q. So now we have this equation of motion. And the key thing we have to remember is that these are amplitudes of basis functions. They're not the displacement of anywhere on the beam, right? They're an amplitude of a shape function. So they don't tell us directly what the displacement of any of these masses are. But instead we would define some kind of shape function, could be anything. And the Q would just set the amplitude of this function. And actually I'm drawing it as if it's bending, but it's actually axial in that case. All right, so that's our equation of motion. So once we have those, we could solve for the response, Q of t, or whatever it is, or find the modes, whatever it is that we're interested in doing. And then the key thing we remember is when we want to go back to physical displacements, that we need to use this key assumption again, right? We're going to use this formula again. So this is our key to relating the QJs to the physical displacements that we're interested in. All right, so that's all there is to it. Just those basic steps and some integrals to evaluate. I guess I should have mentioned this first step also includes choosing the basis functions, psi j, and those need to satisfy the boundary conditions, any displacement boundary conditions that we might have. And the book has tables of suggested basis functions that you can use. So that's not a very difficult step. All right, let's work an example now. And let's say that what we want to do is estimate the response of a rod with a big mass on the end. So this is a rod, so we're talking about axial motion. The rod would be defined by its Young's modulus, its cross-sectional area, its length, its density. And again, just to emphasize, here we're talking about axial motion. So, by the way, if we hadn't yet covered this section, right, we could approximate the system this way, where we would replace the rod with the spring, but this wouldn't have any mass. So one thing we could do with this analysis is to come up with a way of estimating how much of the mass of the rod should we include if we want to have a model such as this. Okay, so let's go through our steps and let's solve this. So our first step is to approximate the displacement with the Ritz series equation there. So we're covered there. And so we'll need to choose a basis function. So let's let our basis functions psi I of x be equal to polynomials x over L to the I power. All right, and by the way, table 1 in chapter 6 is the one that would give you the suggested basis functions, and that's one that's in there. All right, so what we could do then is now we can plug in the formulas. So we're going to go to the book and use these formulas for the terms. So going to the book, we look up and we find the formula. Mjn is the integral from 0 to L psi j psi n rho a dx. plus the summation of any masses times psi j of xn, psi n of xn. All right, that's our formula. And actually, before we dive in too much, let's just take an example just to try to make this clear. So if we plug everything in here, if we wanted the 1, 2 term, or, that's the term there in the mass matrix, right? We'd take x over L to the 1 power for psi j, x over L to the 2 power for psi n, rho a dx, and then in our case we have the mass times the basis function evaluated at the point where the mass is. We'd have L over L to the 1 power, L over L to the 2 power. Right, and this integral we can evaluate, we can simplify it as the integral from 0, give a little more space here, simplify it as the integral from 0 to L, x cubed over L cubed. And if the density and the area are constants, we can actually pull all of those terms out. So we'd have x cubed dx times rho a over L cubed. All right, and here we just get m. All right, and now if we evaluate that integral, rho a over L cubed, this integral will just give us x to the 4th over 4, evaluated from 0 to L, plus m. So basically we get an L to the 4th in the numerator, and what we ended up with is rho AL times 1/4 plus m, right? So that's all there is to it, and especially with polynomials, this is easy enough that we can actually just go and we can evaluate this integral for a general case. So in the general case, this would be x over L to the j power, x over L to the n power, rho a dx, plus the mass times x over L, or L times L over L. These will all be L over L, so this is all just going to be 1. We don't need to do anything more there. And as we did in the previous case, we can write this as x to the, we can combine those two terms, so it'll become x to the j plus n. And let's also pull out our constants. So those would be rho a over L to the j plus n. That's just the sum of two integers. Then we have x to the j plus n dx. All right, and similarly to what we got before, now we'll get x to the j plus n plus 1, so we increase the numerator by 1, and we divide that by, we divide by that numerator and evaluate this from 0 to L. So the L to the j plus n, most of these cancel, and we're left with something similar. Oh, we got plus n. So we're left with rho a L over now j plus n plus 1. And so that's the constant that gave us the 1/4 before, plus the mass that's out on the end. So here's our mjn term. All right. So, so that's all there is to it. I won't go through everything on KJN, but I do just want to mention that now this equation, it's the first derivative of psi j with respect to x, the first derivative of psi n with respect to x, times the Young's modulus times the area dx. And then there's some other terms that we don't have any discrete springs, so I won't include those. Let me just kind of show you what this looks like. So in this case, we need to take a derivative first. So if we have x to the j, the derivative of, so if we had x squared, the derivative would be 2x, right? So we pull down the exponent, we reduce the power by 1. So x to the j would give us j x to the j minus 1, right? And then L is still L to the j. We haven't changed anything there. And then similarly, we'd have n x to the n minus 1, L to the n. All right, so the formulas get a little, get a little different. Maybe you could already start to do that in your head. That ends up being EA over L times NJ over J plus N minus 1. All right, so that's the term for the stiffness matrix. And now we are ready to write our equation of motion. Right, so we can, now we decide how many terms we want. Let's just do a really simple case. If n equals 1, our equation of motion is just m11 q1 double dot k11 q1 equals capital Q. And let's actually just not have a force. We'll just have that equal to 0. So in this case, we'd have rho AL to the 1 plus 1 plus 1, or we'd have 1/3 rho AL plus the mass that's out on the end, all of that times Q1 double dot, and our K11 term, we'd have 1 times 1 over 1 plus 1 minus 1, that all is just 1. So we just have EA over L times Q1, and that's equal to 0. So because it's 1 degree of freedom, we could just immediately solve for the natural frequency. So the natural frequency is just the square root of K11 over M11, or we'll get the square root of EA over L, and then in the denominator we have 1/3 rho AL plus N. All right, and that would be our natural frequency. A couple things to point out. If you remember EA over L, if we had a rod of length L and we applied a force, this is what we would get for the stiffness of the entire rod. So if we go back to our picture, right, we're getting the stiffness of that entire rod coming in, the whole thing, right? So that's the same stiffness we would come up with if we decided to write this as a lumped system, like right here, right? K would just be EA over L. So far, the Ritz series has done basically exactly what we would do if we were approximating this as a lumped system. Notice, though, the mass is not just m, but it's taking 1/3 of rho AL. This is the total mass, right? AL is the volume, or that's the mass of the rod. So the Ritz series is telling us take 1/3 of it, because when that mass, the basis function basically is allowing it to say, when this mass moves, if we have a continuous system here, this part is going to move just as much as the mass, this part will move less, this part doesn't move at all. And so it automatically tells us how much of the mass we should take if we were going to lump it all right here, right? So if we're just going to add a 1/3 rho AL on there to account for that. All right, so we've got a pretty good approximation for the natural frequency. How do we tell how good that is? One thing we can do is we can compare this to the analytical natural frequency you would get if you solve the partial differential equations. And the solution is easiest to look up for the case where m equals 0, so let's just look at that. In that case, we would get, if we look this up, we would get E over rho L squared, square root of that, times pi over 2. And you could read in chapter 7 if you want to see how those are derived. What would we get right here for the case where m equals 1, right? Or m equals 0. We get EA over L times 1/3 rho AL. So the A's cancel. So we could write this as the square root of 3 times the square root of E over rho L squared. Right? So these are both similar. Here, this constant is going to be 1.73. This constant will be 1.57. So, we got something already that's in the ballpark of the exact answer. And that's using only one basis function. Alright? So, pretty easy. Not too hard to do. Alright, so that's all the steps. I guess the only thing we haven't done is talk about physical displacement. So let's talk about that real quick. So this would be step 4. Say we've got this answer now and we want to know what's the physical displacement. Well, if we plot u versus x, we're using a basis function that's x over L. So when x is equal to L, the basis function will be equal to 1, right? So this is our psi of x. And our u of x and t is just that psi of x times psi 1 of x times q1 of t. So I should call that psi 1. So this will be the displacement, and whatever value of q1 of t we have will set the amplitude at the point at the end of the rod. So rather than an amplitude of 1, we'll have q1 of t as our amplitude, right? And every other point will have half that much. So this point here, or we'll have some fraction of that. So in the middle, we'd have 1/2 q1 of t, right? If we went to the 4th point, we get 1/4 q1 of t, and so on. But this basically tells us how every point in the structure is moving, and gives us that approximation. What would the analytical solution be? If we were talking about motion in mode 1, the analytical solution would look like this. So the true, I'll call this phi 1, true, this would be the mode shape of mode 1. It would be given by a function of sine of pi over 2 times x over L. So we're approximating that with a line because we're using a one-term polynomial or a linear function to interpolate. And we get something in the ballpark, but not exact. All right, so there's our example. We'll stop this, and then I'll show you in the next set of slides how we can do that in MATLAB and what that looks like there.